Algebra 1 Unit 7, Lesson 3, Geometric Sequences. In this lesson, we want to identify, graph, and solve problems involving geometric sequences. It's in this unit because geometric sequences are actually exponential functions, but are in a discrete set of points, just like arithmetic sequences where lines are in a discrete set of points where they're not continuous, they come at only certain points. Geometric sequence comes from going from one point in the sequence to the other. We always multiply or divide by the same number each time. So the ratio of two consecutive numbers is always the same. So the second number over the first number will always give me the same thing as the third over the second, the fourth over the third, and so on. The common ratio r is the number multiplied or divided by each time. The points of a geometric sequence, as I said, actually lie on the curve of an exponential function for positive r. Each pair, just like for arithmetic sequences, can be paired with the order number, so it's a discrete function. So this would be, the first term is 3, so we would graph the point 1, 3. The second term is 6, so we would graph the point 2, 6. The third term is 12, so we would graph the point 3, 12. The fourth term is 24, so we would graph 4, 24. And the fifth term is 48, so we would graph 5, 48. So I labeled my scale from 1 to 10, and then I needed to get up. I decided to go, each 4 squares was 12, so each one was 3. That got me up to 60, so 1 was 3, 2 was 6, 3 was 12, 4 was twice that, or 24, and 5 doubled that again, that was 48. If we look, we are multiplying by 2 each time, so b would be equal to 2, as we can see, or we can take any 2 points if we want to find the function and substitute them like we did before. So y equals a times b to the power t, or technically, because this is discrete, we would have the function value at n would be a times b to the power n. So if I substitute the 1.13, 3 is the y value, so 3 would be a times b. 2, 6, 6 equals a times b squared. If I take 6 over 3, that has to be the value of b, which is 2, as I said, because we're multiplying by 2 each time. And then if I substitute that back in for 2, I would get a is equal to 3/2. Or we could have gone backwards by dividing this by 3 and gotten 3/2. So f of n is equal to 3/2 times 2 to the power n, but this is only for n equals 1, 2, 3, and so on. Now I will note that here we put 2 to the power n, but if we wrote this 3/2, this is 1/2, this 2 is 2 to the minus 1, and we could combine that with the 2 and get 3 times 2 to the power n minus 1, which will be our normal way of writing them initially when they come for a geometric sequence, like we had for arithmetic. We added d n minus 1 times. Here we will multiply by r n minus 1 times. So in fact, how can we find the next term? We can use a recursive rule where someone gives us the starting value f of 1, and then to get f of n, we take the term before and multiply by r, or if we do it in sequence notation, someone has to give us a of 1, and then we would find succeeding terms by taking the one before and multiplying by r to get the next one. If we want to jump to any term, we will use the explicit rule, where we start with f1, and then we have to multiply by r n minus 1 times to get to the nth term, and that's true whether you put it in function notation or sequence notation. This can always be written in exponential form, which doesn't have an n minus 1 in the exponent, by simply rewriting that this r to the n minus 1 is r to the n times r to the minus 1, and that r to the minus 1 is, which is 1 over r, gets combined with that first term, so it would be a1 over r would be our initial value, and then b is simply the same as r. So how is a geometric sequence different from other exponential functions? As I mentioned at the beginning, exponential functions are connected, they're continuous, but the domain and range of a geometric sequence is only a discrete set of points, so they're not connected on a graph. And for a geometric sequence, r doesn't have to be positive, but if it's negative, it's not exponential. Here as an example, we have a bungee jumper who jumps from a bridge. The table shows the bungee jumper's heights above the ground at the top of each sequence. These heights form a geometric sequence. Write the recursive rule for the sequence. So first of all, we need r. We would take whatever the second term is and divide by the first term. So that's 80 over 200, or 32 over 80 would work the same. 80 over 200 is 2/5. The initial value at time 1 is 200. So we start off with 200, and then a to the n is 2/5 of a to the n minus 1. If we want the explicit rule, we get a to the n is 200, and then we multiply by 2/5 n minus 1 times. We would be done, except that it asks us to have this in exponential form. So we take this minus 1 and split it from the n, 2/5 to the minus 1, and combine with that 200. If we multiply that, that will give us 500 times 2/5 to the power m. So this is in the normal sequence form, and then this is in exponential form. What is the bungee jumper's height at the top of the fifth bounce? We now need to put 5 into that function. The fifth term will be 500 times 2/5 to the power 5, or 5.12. The jumper's height is about 5.1 feet. If we want to graph this as a geometric sequence, again, we're pairing those with the first term is 200, and we would graph 1, 200. The third term is 80. The third term, we had 32, and then we were taking 2/5 of that, and that would give us a value here, and 2/5 and 2/5. You could continue to find those values. After the fifth bounce, there's very little change in the height, so it wouldn't be very fun anymore because you're not going to be really going up and down. So I've shown here how to calculate those values, and then I've graphed them. Consider the geometric sequence 27, 9, 3, 1. Write the recursive rule for the sequence, then write an explicit rule for the nth term of the sequence. Give the rule in sequence form, power n minus 1, and in exponential form to the power n. So r is equal 9/27, which is 1/3. The sequence form, an is equal 27, which is the initial value, and then we're going to multiply by 1/3 n minus 1 times for n equals 1, 2, and onwards. If we wanted an exponential form, we split out a power of minus 1 from the n. Then we combine that with the initial number, which will give 27 times 3 and get 81. Or you could just consider, if we're dividing by 3 each time here, we would multiply to go back to find the initial one, which would give us an exponential form.